The information paradox, one of the greatest mysteries in modern physics. The question is, what happens to information when an object falls into a black hole? A black hole is a strange region of space where gravity is so strong nothing can escape, not even light. That means we can't see inside. We can't know what's happening in there. And that's where the problem begins. When an object falls into a black hole, all information about it disappears forever. But quantum mechanics, a core foundation of physics, says the opposite. Information can never be destroyed. So, what's going on? If a black hole makes information vanish, then it's violating the most basic principle of quantum theory. That's the information paradox, and it has puzzled scientists for decades. Why does it matter so much? Because the information paradox isn't just about black holes. It's about how the universe works. Modern physics stands on two main pillars: quantum mechanics, which explains the tiniest things, like particles and atoms, and it says, information is always preserved, no matter how an object changes or decays. Meanwhile, general relativity, which describes gravity and massive objects like stars or black holes, and it has no rules about preserving information. Both theories are correct. Both have been proven. But when it comes to black holes, they clash. And that's a serious problem, because these two theories are the foundation of all modern physics. If they can't work together, we need a new theory, one that explains both the very small and the very large, what scientists call quantum gravity. But why do black holes create this paradox? To understand it better, look at something called the event horizon. It's the boundary around a black hole. Once you cross it, everything gets trapped forever. Nothing can escape, not even light. That's why it's completely black. In the 1970s, Stephen Hawking discovered something unexpected. Black holes aren't completely silent. It emits energy, slowly, weakly, but it's real. It's called Hawking radiation, caused by quantum effects happening near the edge of the event horizon. Over time, this radiation causes the black hole to lose mass, to shrink, and eventually disappear. But there's a problem. Hawking radiation doesn't carry any information. It's completely random. It contains no data about what fell inside. And if the black hole vanishes entirely, then all the information inside vanishes with it. Quantum mechanics says that can't happen. Information is not allowed to disappear. So, what's really going on? This is the heart of the information paradox. Why does losing information matter so much? It might not sound like a big deal, but in physics, it's a critical blow. If black holes truly erase information, then it means quantum mechanics, one of the most successful theories ever created, might be wrong or incomplete. It also means we might be misunderstanding how the universe works, not just at the edge of a black hole, but everywhere. And that leads to even bigger questions. If information can be lost forever, can we ever truly understand the past? Does cause still lead to effect? Or are they just illusions? In a universe that's fundamentally unpredictable, if the universe can lose information, then maybe there are things we can never truly know. The issue no longer stays in the lab. It touches how we think about reality. So what have scientists done? They've come up with many ideas to solve this paradox, but none have been proven. Here are the most notable theories. The holographic principle. This theory suggests the information about everything that falls into a black hole is not lost, but stored right on its surface. The event horizon is where all the information gets recorded, like a skin wrapped around the black hole. The information isn't inside, but encoded on the outside. According to this theory, the inside is just a 3D projection of the data on the surface. If true, information isn't destroyed. It's just stored in a way we don't yet fully understand. Hawking radiation might carry information. Some scientists believe Hawking radiation is not entirely random. They suggest it may contain tiny fragments of the original information. Bit by bit, that information could leak out as the black hole slowly shrinks. Over time, it doesn't just emit light, it speaks. Black hole remnants. Another idea: black holes don't fully vanish. As they evaporate, they might leave something behind. A small, stable object holding all the internal information. Like a final encoded particle, not erased, just hidden. New laws of physics. Maybe this paradox is a signal that our current physical laws are still incomplete. Perhaps we need an entirely new framework, one strong enough to unite quantum and relativity, quantum entanglement and space-time. A more recent hypothesis. It proposes that particles inside a black hole might be quantum entangled with regions elsewhere in the universe. A kind of invisible link, not through light, but through the fabric of space-time itself. If true, information could escape the black hole through pathways we haven't yet recognized. So, what can we learn from all this? The information paradox isn't just a question of physics. It's a reminder that we still know very little about the universe. That even our strongest theories might have cracks. It also reminds us of the deep connection between every branch of physics. To understand black holes, we need to combine quantum, relativity, and maybe things we've never explored before. The information paradox leaves us with something else, a greater challenge, more direct, heavier. It forces scientists to rethink everything, not just about black holes, but about our entire understanding of the universe. If information can be erased, then is memory even real? Does cause still lead to effect? Or is everything just a chain of untraceable events? Physics used to be numbers, but now it's a question of existence. The firewall paradox, a new paradox, directly tied to the edge of a black hole. Traditionally, it's believed that the event horizon is an unremarkable region. No tremble, no fire, no wall. You pass through it, and only deeper inside do strange things begin to happen. But the firewall hypothesis says otherwise. It suggests that right at the edge, the event horizon, there may exist an extremely powerful wall of energy, a blazing region, a violent barrier. If that's true, anything falling into a black hole would be incinerated instantly. No time to feel anything else. No chance to go deeper. No more gentle fall. And that's the problem. Einstein's general theory of relativity doesn't allow for this. It says, falling into a black hole should feel uneventful at first. You wouldn't even notice. There would be no dramatic physical effects. This is based on the equivalence principle, which means all observers, wherever they are, falling or stationary, should see the same physical laws. According to that, you could fall through the event horizon without noticing a thing. But the firewall says otherwise, very otherwise. It claims right at the event horizon is where the break occurs, where everything collapses, and you wouldn't fall into silence. You'd crash into a wall and vanish. So, where does this energy come from? The firewall, if it exists, would be the result of severing quantum connections, known as quantum entanglement, between the particles inside the black hole and those flying outward, as Hawking radiation. Hawking radiation is what causes a black hole to lose mass over time. It's generated by quantum effects right near the edge. It's how a black hole slowly evaporates. But for information to escape through this radiation, the quantum links between particles must be cut. And when those links are broken, a massive amount of energy is released. The result? A firewall. If the firewall is real, it would destroy any object trying to cross the event horizon. This directly contradicts what Einstein predicted. One side says, falling in feels normal. The other says, falling in means burning alive. Both can't be right at the same time. And this is the firewall paradox, a major clash. The firewall paradox isn't just a technical disagreement. It exposes a deep conflict between the two most powerful theories ever created, quantum mechanics and general relativity. Both are correct. Both have been confirmed by thousands of experiments. But when it comes to black holes, they don't agree. And this is why. The firewall paradox matters. It reveals a major gap in our current understanding of the universe. At least one of these theories must be incomplete. Or we're missing a deeper answer, a theory that could unite them both. And it doesn't stop at physics. This paradox also challenges how we understand space-time. If the firewall exists, it means space-time is not smooth or continuous the way Einstein predicted. Instead, it might break down, right at the edge of a black hole, under the most extreme conditions. So is there any solution? Several proposals have been made, but so far, none have been proven true. Here are the main approaches. The firewall is real. Some physicists believe the firewall is necessary to protect the rules of quantum mechanics. If that's true, we'd have to accept that Einstein was wrong at the event horizon. No more gentle fall. No more nothing special. Information escapes without a firewall. Another view suggests information can still escape through Hawking radiation without needing a firewall. But that requires an entirely new way to explain how information gets encoded within the radiation itself. Complementarity. An explanation from string theory. It says, the issue lies in perspective. From the outside, we see information escaping as Hawking radiation. But from the viewpoint of someone falling into the black hole, everything feels smooth. There is no firewall. Both perspectives are valid, but they can't be observed at the same time. New physics. Some scientists believe this paradox is clear evidence that we need an entirely new theory of physics, a theory that unifies quantum mechanics and general relativity, often referred to as quantum gravity. This theory, if it exists, might be the key to resolving the paradox and bringing us closer to the biggest answers in physics. What does the firewall paradox teach us? It's not just a technical issue about black holes. It forces us to reconsider our entire understanding of the universe. It shows that even the best theories might still fall short. Black holes aren't just extreme objects in space. They are gateways to the deepest mysteries of reality. By studying them, we don't just learn about gravity or quantum mechanics. We begin to explore the limits of human knowledge. The firewall paradox is a humbling reminder. The universe is always more complex than we imagine, and there is still so much that science cannot yet reach. There is still so much we don't know. Solving paradoxes like the firewall could unlock major breakthroughs in how we understand space-time, gravity, and the quantum world. It could be the key to building a unified picture of how the universe truly works. The no-hair theorem, one of the simplest, yet most controversial, ideas about black holes. It states that all black holes, no matter what they're made of, can be described by just three properties: mass, charge, spin. It doesn't care about the rest. A star, a cloud of dust, or even a spacecraft. Once it falls into a black hole, every unique feature is erased. Only three things remain: mass, charge, and spin. No hair. The term no hair is a metaphor. Hair represents unique traits, the distinguishing marks of matter. But this theorem says black holes have no hair. They retain no trace of what fell into them. It leads to a strange conclusion. Any two black holes with the same three properties will be identical. Whether formed from a collapsing star or a cloud of gas and dust, the outcome is the same if those three values match. That makes black holes easier to describe. But it also creates a serious problem. Where does the lost information go? Why does the no-hair theorem matter? Because it directly relates to one of the biggest questions, the information paradox. According to quantum mechanics, information is never destroyed. Whether it's chemical composition, structure, or the history of matter, it must exist in some form. But the no-hair theorem says everything gets erased. So, where does the information go? If it's truly lost, that directly contradicts quantum mechanics. This is the conflict. On one side is Einstein's theory of relativity. On the other is quantum mechanics. Both are correct elsewhere. But when it comes to black holes, they don't align. And to understand the universe, we have to resolve this contradiction. So is there any evidence for the no-hair theorem? Scientists have tested it through observation. One of the strongest methods is tracking gravitational waves. These are ripples in the fabric of space-time, created when black holes collide. In 2015, the LIGO experiment detected gravitational waves for the first time. They came from the merger of two black holes. The result? The properties of the resulting black hole matched the predictions of the no-hair theorem exactly. Since then, many other observations have supported it. Black holes behave exactly as the theory predicts. They retain three properties and leave no other trace: challenge and controversy. The no-hair theorem is widely accepted, but it's not without flaws. One of its key assumptions is that black holes exist in isolation, unaffected by their surroundings. In reality, that's rarely true. Most black holes interact with gas, dust, and nearby objects. These interactions could influence their properties. Soft hair. Some physicists have proposed that black holes might possess subtle, delicate features they call soft hair. These features could preserve information in ways we don't yet understand. If true, this idea directly challenges the no-hair theorem. But it could also help solve the information paradox. The bigger issue: quantum gravity. The no-hair theorem is based on general relativity. It doesn't account for quantum effects. To fully understand black holes, we need a theory of quantum gravity, a framework that unites both quantum mechanics and relativity. Only then can we know whether black holes are truly simple or hiding far more beneath the surface. Why does the no-hair theorem matter? Because it raises a fundamental question. If black holes erase information, does that mean quantum mechanics breaks down? Or is there still a way for information to be preserved? We just haven't found it yet. This question isn't just theoretical. It shapes how we understand cause and effect and the nature of reality itself. Beyond that, the theorem has practical value. If all black holes share the same three basic properties, they become easier to describe and predict. This helps scientists study how black holes form and evolve. What do we learn? The no-hair theorem reveals the tension between simplification and complexity in nature. It helps us model black holes, but also pushes us to the edge of knowledge. It works well within the framework of relativity, but once we enter the quantum realm, it may no longer be enough. As science moves forward and paradoxes come to light, the no-hair theorem will remain a vital part of our attempt to understand the universe. Hawking radiation and black hole evaporation. In the 1970s, Stephen Hawking introduced a shocking idea. Black holes are not completely black. They emit a very faint type of energy, known as Hawking radiation. This discovery completely changed how we understand black holes, quantum theory, and the very structure of the universe. But it also raised a new question. What happens to the information about everything that fell in when the black hole disappears? So what is Hawking radiation? First, we need to revisit the definition of a black hole. A black hole is a region of space where gravity is so strong, even light can't escape. That's why it's completely black. It doesn't emit light, doesn't reflect, and sends no information outward. Another theory suggests that when a black hole evaporates, it leaves behind a small remnant, called a remnant. This remnant could retain all the information that once fell into the black hole. But it opens up new questions. What exactly is a remnant? Is it stable? How does it function? New physics. Some scientists believe the information paradox may be a sign that we don't yet fully understand physics. Maybe a new theory is needed to unite quantum mechanics with general relativity. It's called quantum gravity. This theory might explain how information is preserved during black hole evaporation. Another idea: information might escape to another universe. If true, the black hole doesn't destroy information. It simply transfers it to a place we cannot reach. Why does this matter? The discovery of Hawking radiation shows black holes aren't as simple as we once thought. They're not just places where everything vanishes. They are complex systems bridging the two greatest theories in modern physics: quantum mechanics and relativity. The information paradox isn't just a puzzle about black holes. It's a clear sign that quantum mechanics and general relativity don't fully agree. Solving this paradox could lead humanity to a unified theory that explains both the incredibly small and the incredibly large. The mystery continues. Scientists still don't know what happens to information when a black hole completely evaporates. But in the journey to find answers, they've expanded our understanding of black holes, of quantum mechanics, and of the nature of reality. Even though the puzzle remains unsolved, it continues to inspire new ideas and discoveries. The singularity paradox. One of the greatest mysteries in modern physics is tied to a concept known as singularity. It's a tiny point at the center of a black hole where the laws of physics break down. At this point, gravity becomes infinite, and space and time lose all meaning. Physicists don't know how to explain this. That's why singularities are among the hardest problems in understanding how the universe works. So what is a singularity? It forms when a massive star dies. Throughout its life, the star burns nuclear fuel to produce energy, maintaining balance. But eventually, the fuel runs out. The star no longer has enough pressure to resist its own gravity. The result? It collapses. If the star is massive enough, this collapse doesn't stop at a neutron star, but forms a black hole. Inside the black hole, all the star's matter is compressed into a tiny point with infinite density and zero volume. This is the singularity. The gravity there is so intense that even light cannot escape. That's why a black hole is completely dark. And here's the issue. Infinite density and zero volume have no practical meaning in physics. They're not measurable values. They're just the result of mathematics breaking down in our current models. Here's the problem. We can't measure or observe infinite quantities in the real world. Numbers like infinite density or zero volume tell us that our current physical models have hit a limit. This is a conflict between the two greatest pillars of modern physics. On one side is general relativity, Einstein's theory, which explains how massive objects like stars, planets, and black holes curve space and time. This theory predicts that singularities must exist when gravity becomes extremely intense. It claims that space and time themselves are crushed completely at the singularity. On the other side is quantum mechanics. This theory describes the behavior of the extremely small, like electrons, photons, and fundamental particles. It cannot handle infinite values, and it can't model a point with zero volume. When a singularity appears, quantum mechanics breaks down. At the singularity, both theories, relativity and quantum mechanics, cease to function. And that's why it's often called a point of no return in our current understanding. Why does the singularity paradox matter? It's not just about black holes. It challenges the entire framework of physical law in the universe. If singularities truly exist, that means the universe doesn't follow consistent rules anymore. How can a point exist that the laws of physics themselves can't explain? But if singularities don't exist, then what exactly is at the center of a black hole? And there's more. The Big Bang theory also begins from a state much like a singularity, a tiny, ultra-dense, ultra-hot point. If we can understand the singularity inside a black hole, we might uncover clues about the origin of the universe. Solutions? Physicists have proposed many ideas to resolve the singularity paradox. Each one requires going beyond the limits of current physics. Quantum gravity. This is the general name for any theory that could unify relativity and quantum mechanics. It might reveal that singularities aren't truly infinite. They're just states we don't yet understand. String theory. A strong contender in the quest to explain singularities. Instead of point-like particles, it proposes that matter is made of tiny, vibrating strings. These strings have a finite size, preventing infinite density from forming, creating a smallest possible scale for both matter and energy. Loop quantum gravity. Another direction. It suggests that space and time aren't continuous, but built from discrete chunks. And if that's true, when matter is compressed to the limit, it wouldn't form a singularity. It would bounce back. Instead of collapsing infinitely, matter would hit a minimum scale and then expand again. Cosmic censorship hypothesis. Some scientists have proposed another idea. Singularities might exist, but are always hidden behind an event horizon. There, they can't influence anything outside. This idea is called cosmic censorship. The cosmic censorship hypothesis goes even further. It suggests that singularities aren't physical entities. They're just products of mathematics, a phenomenon that exists in equations, not in the real world. Some scientists disagree. They believe the extreme conditions inside black holes don't create singularities, but generate strange states of matter. These states might form a special matter core, avoiding the infinite values predicted by general relativity. If true, these matter cores would offer a more realistic description of what lies inside a black hole. So what do we learn from the singularity paradox? It's not just a puzzle, it's a doorway into unexplored territory. It reminds us our current understanding of the universe has limits, and that, if we want to go further, we need new ideas. The singularity paradox also shows how different fields of science are deeply connected. Relativity works well for large-scale things, like planets, stars, galaxies. Quantum mechanics, on the other hand, describes the small particles, atoms, photons. But singularities lie at the boundary between these two worlds. They force us to seek a theory that unifies everything. In the end, the paradox raises a profound question. What happens to space and time at a singularity? Is there a limit to what humans can know? If we keep pursuing these questions, we may get closer to the true nature of the universe. Next up, the black hole entropy paradox. This is a major paradox, and it forces us to rethink some of the most basic rules of physics. This time, the problem lies in something called entropy. Entropy is a measure of disorder or complexity within a system. And here's the strange part. The entropy of a black hole is unlike anything else in the universe. For most objects, entropy is proportional to volume, meaning the space they occupy. But for black holes, entropy is proportional to surface area. More specifically, the area of the event horizon, the invisible boundary beyond which nothing can escape. This doesn't match the normal laws of physics, and it creates a paradox. So what is entropy? Let's take a simple example. A neatly stacked pile of books equals low entropy, because there's only one way to arrange them in perfect order. A messy pile of books equals high entropy, because there are countless ways to create that mess. In physics, entropy is a measure of how many possible states a system can be in. And in most physical systems, entropy increases as the system gets larger. If there are more particles, more space, there are more ways to arrange them, higher entropy. So, in the ordinary world, entropy usually scales with volume. But black holes don't follow that rule. In the 1970s, physicist Jacob Bekenstein proposed a shocking idea. After Bekenstein, Stephen Hawking took it even further. He discovered that black holes aren't completely black. They emit a form of energy. It's called Hawking radiation. Over time, this radiation causes a black hole to slowly lose mass, meaning a black hole can evaporate. From these discoveries, a surprising conclusion emerged. The entropy of a black hole does not depend on its internal volume. It only depends on the area of its event horizon. In other words, surface area determines entropy, not the space inside. The formula shows that, as the event horizon grows, entropy increases with it. Even though we assume entropy relates to volume, with black holes, that no longer applies. And this very difference gave rise to the black hole entropy paradox. Why is this paradox so important? Because it challenges the most fundamental ideas in physics. First, entropy and thermodynamics. Entropy is a core concept in the study of heat and energy, but the strange behavior of black holes suggests the laws of thermodynamics may no longer hold under extreme conditions. Second, quantum mechanics and gravity. Black holes are products of relativity, which describes gravity, but their entropy hints at hidden quantum processes inside. It's as if two theories, once separate, are converging at the black hole. Combining quantum mechanics and relativity is one of the greatest challenges in modern physics. Third, the nature of information. If entropy depends on surface area, that suggests all the information inside a black hole is somehow stored on its surface. That idea is strange, and it could change how we think about space, time, and reality. Lastly, the limits of knowledge. The paradox shows the universe doesn't work the way we think, especially in extreme places like black holes. We may be missing a crucial piece. So what solutions have scientists proposed? They've proposed several ideas, none of them proven yet, but each one opens up fascinating possibilities. First idea, the holographic principle. This principle suggests that all the information in a region of space can be encoded on its boundary surface. For black holes, this means the information inside is actually stored on the event horizon. And the principle goes even further. The entire universe might operate the same way. The three-dimensional objects we see could just be projections of two-dimensional information. Second idea, string theory and quantum gravity. String theory, a candidate for quantum gravity, proposes that black holes are made of tiny vibrating strings. The way these strings are arranged might explain why entropy depends on surface area. This theory also supports the idea that information is stored on the event horizon, not inside. Third idea, black hole microstates. Some scientists are trying to calculate the tiny quantum states inside a black hole. They treat the black hole as a thermodynamic system. If they can count these states, they may be able to show why entropy relates to the event horizon. Finally, new laws of physics. The entropy paradox might be a sign that our current laws of physics are incomplete. We may need new rules to explain the connection between entropy, quantum mechanics, and gravity. And from that, the black hole entropy paradox opens a much bigger door. It's not just about black holes. It raises questions about how the universe operates at its deepest level. First is the question of information and reality. The paradox shows information doesn't necessarily have to exist inside the volume of space. It might exist only on the surface. This idea reshapes how we think about storing and transmitting information in the universe. Next is the need for a unified theory. If we want to truly understand black holes, we need a framework that combines quantum mechanics and relativity. The paradox is clear evidence that these two theories aren't enough on their own. The question is the universe a hologram? The entropy of a black hole depends on surface area, not volume. This supports the idea that the three-dimensional universe we live in might just be a projection of two-dimensional information. A strange hypothesis, but one that more physicists are taking seriously. Black holes are also the universe's extreme laboratories. They are places where classical physics breaks down, where the usual rules no longer apply. And because of that, we might discover new physical laws, ones we've never seen before. But why hasn't this paradox been solved yet? Even after decades of research, the black hole entropy paradox remains a mystery. It challenges the most fundamental concepts: entropy, information, space, and time. If solved, we might unlock new insights about the universe and possibly spark major breakthroughs in modern physics. Black holes, once seen as strange and simple objects, are now considered the key to understanding reality. They are not just points in space. They are gateways to the deepest questions about how the universe truly works. Next, the time dilation paradox. This is one of the most striking paradoxes, and it challenges our understanding of how time behaves near a black hole. It begins with a seemingly simple idea. Time doesn't flow the same for everyone. When someone falls into a black hole, their experience of time feels completely normal. But for a distant observer, that falling person appears to slow down and almost stop. They seem to never fully disappear. This strange difference challenges how we think about time and reality. So what is time dilation? It's the phenomenon where time flows at different rates, depending on your position and speed. According to Einstein's general theory of relativity, massive objects, like black holes, can bend space-time. That bending slows down time near them. The stronger the gravity, the slower time moves. Black holes are the most extreme example. Their gravity is so intense that near them, time nearly stops. Right at the edge of a black hole, known as the event horizon, time appears frozen from the point of view of a distant observer. And this is where the paradox begins. There are two different perspectives on the same moment in time. Two people, two completely different experiences of time. The person falling into the black hole feels time passing normally. They don't notice anything unusual. No signal marks the crossing of the event horizon, and eventually, they reach the center of the black hole, a place known as the singularity, where gravity becomes infinite. But for the distant observer, everything looks completely different. As the person approaches the event horizon, they begin to slow down, dramatically, as if frozen in space. From that point of view, the falling person never crosses the boundary. Instead, their image stretches, fades, and disappears into the light bent by gravity. This is the paradox. From inside the black hole, the falling person has already crossed. From the outside, the observer sees. They never cross at all. So who's right? According to Einstein's theory of relativity, both are right, within their own frame of reference. Time and space are not absolute. They behave differently, depending on where you are. And this is the heart of the time dilation paradox. It's not just a strange phenomenon. It's a sign that time is not fixed. It can run fast or slow, depending on gravity and your position in the universe. We're used to thinking of time as something unified, ticking the same for everyone. But this paradox completely denies that. And it leads to an important question. If, from the outside, nothing can ever cross the event horizon, then how does a black hole grow? How does it absorb matter? How does it gain mass? Scientists know black holes really do grow over time, but this paradox raises a problem. How does matter fall in if, from the outside, it never crosses? The answer is still being sought. But one thing is clear. Reality isn't the same for everyone. Two people can witness the same event, but see completely different outcomes, and both are correct. This idea may sound strange, but it's the foundation of relativity. It's not some distant theory. We use it every day. The clearest example, GPS. Satellites orbit the Earth, where gravity is weaker. So, their clocks run faster than clocks on the ground. If not corrected, the navigation system would be off by kilometers. It's living proof that time is not absolute. So, is there a solution to this paradox? Scientists have proposed many hypotheses. Here are some of the most notable explanations. Relativity of perspective. The simplest explanation. Each observer is correct within their own frame of reference. Time and space change depending on position. This difference isn't a contradiction. It simply reflects the strange nature of the universe. Black holes still grow. Even if the outside observer never sees matter cross the edge, real-world observations show black holes do grow. And that means the process is still happening, even if we can't directly see it. The mass and energy of falling matter still get added to the black hole's total mass. But there's another problem: Hawking radiation. Stephen Hawking proposed that black holes aren't completely black. They emit radiation, very weak, but real. This radiation causes black holes to slowly lose mass, and over time, they will completely evaporate. The question is, if nothing ever crosses the event horizon, how can it evaporate? That question still has no clear answer. Some physicists believe quantum mechanics might offer an explanation. Quantum effects may store information right on the surface of the event horizon, meaning part of the falling object remains on the surface, even as the rest continues inward. This forms the basis for a larger idea, the holographic principle. It proposes that all the information about an object can be encoded on its surface, like a 2D projection that holds all the data of a 3D world. From the outside, the object gets stretched out and stored on the event horizon. From the inside, it continues falling toward the center. This dual nature helps reconcile the two conflicting perspectives. So, what does this paradox teach us? First, time doesn't flow in a simple, fixed way. It's tied to space and gravity. Massive objects like black holes bend and stretch time itself. This effect creates strange phenomena that defy human intuition. We also learn something else just as important. perspective matters. In relativity, two observers can witness completely different events, and both are right within their own frame of reference. This forces us to see reality in a new way. No more absolutes, only relative perspectives. Black holes are part of that, but also a gateway to something bigger. They're not just objects that pull everything in. They are natural laboratories, helping us better understand time, space, and gravity, and that knowledge impacts everyday life. Example, the GPS system. Without time correction for dilation effects, GPS would be inaccurate. Hundreds of thousands of people would get lost every day. In other words, the time dilation paradox isn't just a curiosity. It's a gateway to the strangest nature of the universe. It shows us that time and reality are more flexible than we think. And from here, a new hypothesis has emerged: the white hole. It's an idea not yet proven, but being taken seriously in theoretical physics. If a black hole pulls everything in, then a white hole does the opposite. It pushes matter and energy out and allows nothing to go in. Black holes have been confirmed by observation. White holes have not. They remain a theoretical idea. But if real, they could teach us a great deal about how space and time truly function, and maybe about the true origin of the universe. So what exactly is a white hole? A white hole is a concept born from the same equations that led us to black holes. Einstein's general theory of relativity. Black holes form when a star collapses under its own gravity. The result, a region of space where nothing, not even light, can escape. A white hole is the opposite. It's a region of space that continuously ejects matter outward and doesn't allow anything to enter. Imagine a black hole as a one-way trap. Once you cross its boundary, called the event horizon, everything is pulled inward and disappears forever. A white hole is the reverse. It's like a one-way fountain. Instead of pulling matter in, it sprays matter and energy outward, and nothing can get in. It sounds like it goes against everything we know about gravity. So where did this idea come from? It comes from the same mathematical framework that describes black holes. In 1916, Carl Schwarzschild solved the equations of general relativity developed by Einstein. The result gave us the first model of a black hole. But interestingly, those same equations also suggest the possibility of a white hole. White holes use the same space-time geometry as black holes, but with one major difference: time runs backward. If a black hole is the process of matter collapsing inward, then a white hole is matter exploding outward. This idea aligns with a core principle in physics: time symmetry. This principle says the laws of physics don't change even if time flows in reverse. However, black holes have been confirmed through indirect observation, but white holes remain a complete unknown. They may exist only in math, not in the real universe. But there's an even more intriguing question. Can a white hole be connected to a black hole? Some scientists believe black holes and white holes might be two sides of the same entity, linked together in ways we don't fully understand yet. From this, a new concept was proposed: a wormhole, or Einstein-Rosen bridge. A wormhole is a hypothetical tunnel in space-time. It could connect a black hole to a white hole. According to this theory, matter falling into a black hole would pass through the wormhole and exit on the other side, through a white hole. That other end might be in a different part of our universe, or even in a completely different universe. However, keeping a wormhole stable is extremely difficult. It would require exotic matter we've never observed. Another idea suggests a white hole might be the final stage of a black hole. Black holes don't last forever. According to Hawking's theory, they emit extremely weak radiation and slowly lose mass over time. Eventually, they evaporate completely. So the question is, what do they become? Some physicists propose they might transform into white holes. If that's true, all the matter and information once absorbed would be released back into the universe. And if so, this could help solve the black hole information paradox. And there's an even bigger idea. The Big Bang might actually have been a white hole. According to this hypothesis, our entire universe was born from an explosive event. All matter and energy were ejected from a single point, and that point might have been a white hole. If true, this could completely change how we understand the origin of the universe, and beyond that, could there be more universes? Each universe, born from its own white hole. This idea sounds like science fiction, but it's being seriously debated in modern theoretical physics. Though fascinating, white holes remain a purely speculative hypothesis. They face several major challenges. First, no observational evidence. Unlike black holes, we have no indirect observations of white holes. Black holes are detected by their effects on nearby stars and the light emitted as matter gets pulled in. White holes are the opposite. No one has ever seen them. For now, this idea exists only in mathematical equations. Second issue, stability. In many scientific models, white holes are unstable. If they constantly expel matter and energy, they would collapse very quickly. Or worse, transform into black holes if they interact with surrounding matter. Third issue, causality. White holes raise a strange paradox. They eject matter, but the origin of that matter is unclear. The effect happens without a known cause. This conflicts with how we understand cause and effect in physics. So why are white holes still important? Even if they don't exist, studying them still holds value. They force scientists to think about the most extreme conditions in the universe, and they challenge the boundaries of our current understanding. Exploring the white hole hypothesis helps us dive deeper into space-time, the nature of gravity, and how time truly operates. White holes also relate to one of the biggest questions in physics. How can we combine quantum mechanics, the physics of the very small, with general relativity, the physics of the very large? If white holes can be connected to black holes, they might offer clues about quantum gravity, a missing piece to unify all of modern physics. And ultimately, the idea of white holes sparks imagination. Could our universe have been born from a white hole? Could there be other universes linked through wormholes? These questions remain unanswered, but they drive humanity further on its journey to explore the cosmos. The ER equals EPR hypothesis, one of the boldest ideas in modern physics. It connects two concepts that once seemed completely unrelated: wormholes and quantum entanglement. In 2013, two physicists, Juan Maldacena and Leonard Susskind, proposed a groundbreaking idea. They suggested that these two phenomena might actually be one and the same. The core idea goes like this. Each pair of entangled quantum particles could be connected by a tiny wormhole, also known as an Einstein-Rosen bridge. This connection isn't meant for travel or sending messages, but it reveals a profound link between the behavior of quantum particles and the structure of space-time. To understand it better, we need to break it down into two parts, ER and EPR. ER stands for Einstein-Rosen. It refers to wormholes, theoretical shortcuts in space-time connecting two distant points. Einstein and Nathan Rosen proposed this idea in 1935 within the framework of general relativity. EPR, on the other hand, relates to quantum entanglement. In quantum entanglement, two particles can become so linked that the state of one instantly affects the other, no matter how far apart they are. The ER equals EPR hypothesis suggests these two ideas aren't separate. They are two perspectives on the same phenomenon. Entangled quantum particles might be connected by microscopic wormholes. These wormholes are far too small for anyone to pass through, but they still represent a geometric link in space-time. Where did this idea come from? It builds on two earlier discoveries by Einstein. First, the Einstein-Rosen bridge, a mathematical concept proposed in general relativity. Einstein and Nathan Rosen introduced this idea as a mathematical solution linking two regions of space-time together. At the time, wormholes were purely theoretical. Around the same period, Einstein, along with Boris Podolsky and Nathan Rosen, was also describing a phenomenon called quantum entanglement. They called it spooky action at a distance, because particles could instantly affect each other even if separated by billions of light years. In 2013, Juan Maldacena and Leonard Susskind made a bold proposal. They suggested the quantum entanglement between particles might actually be a tiny wormhole connecting them, a physical connection, not just a phenomenon. In other words, they combined two of Einstein's own ideas into a new concept. Why does this matter? Because it links two separate branches of physics that have remained apart for decades. General relativity describes gravity and massive objects like stars and black holes. Quantum mechanics explains the behavior of extremely small particles like atoms and photons. Both are incredibly accurate, but they don't work together. The ER equals EPR hypothesis suggests that these two worlds might connect on a deeper level. If true, it could be the first step toward a unified theory, quantum gravity. How does this relate to black holes? Black holes are where these two worlds of physics intersect most intensely. According to the ER equals EPR hypothesis, two black holes could be quantum entangled. In that case, they would be connected by a wormhole, not for travel, not for communication, but as a hidden connection within space-time. Hawking radiation and the information paradox. Black holes emit Hawking radiation and slowly evaporate over time. The problem is, if information falls into a black hole, is it lost forever? The ER equals EPR hypothesis offers a solution. If the particles emitted as Hawking radiation are quantum entangled with the black hole that absorbed the original information, then that information might be preserved. The connection between quantum entanglement and the geometric structure of space-time helps decode one of physics' greatest mysteries. But there are still many questions. The ER equals EPR hypothesis is still just that, a hypothesis. We can't yet test it. Wormholes, if they exist, are far too small to observe with current technology. This makes real-world experimentation nearly impossible. What's more, it works well in simplified models like theoretical black holes. But can it apply to more complex systems, or in real-world conditions? The answer remains unclear. The ER equals EPR hypothesis is one piece of the larger puzzle of quantum gravity, and scientists are still trying to figure out where exactly it fits. Other theories, like string theory or loop quantum gravity, are also trying to explain extreme phenomena in the universe. But ER equals EPR offers an entirely new approach. It's not just a mathematical tool. It's a different way of thinking about the universe. It proposes that the geometry of space-time, wormholes, and quantum entanglement are not separate entities. They're deeply connected in structure, in behavior, and in information. This hypothesis blurs the old boundary between the two pillars of modern physics: general relativity and quantum mechanics. It encourages physicists to think beyond the conventional and to search for unexpected connections between fields that once seemed unrelated. The success of ER equals EPR is also an example showing that scientific breakthroughs sometimes happen when we dare to combine opposing ideas. Maldacena and Susskind have opened a new door to even deeper cosmic mysteries. And perhaps the biggest lesson here is the universe is full of strange connections, and sometimes the answers lie in places we never thought to look. The white hole hypothesis. If a black hole is where everything gets pulled in, even light, then a white hole is believed to be the exact opposite. It ejects everything outward, like a cosmic fountain of matter. The idea may sound strange, but theoretically, it fits perfectly within mathematical models. Some scientists even believe that white holes could give birth to new universes. Imagine this: our universe might have started from a powerful eruption of matter, just like how a white hole works. If a black hole compresses space and time into a point, then a white hole expands it back out. In terms of models, a white hole is the time-reversed version of a black hole. Inside a black hole, the event horizon is the point of no return. Inside a white hole, nothing can cross in from the outside. You can't approach a white hole from the outside, and everything inside can only escape outward. White holes arise from the very equations of general relativity, just like black holes. But the difference is, they've never been observed in reality. They exist on paper as a logical consequence of mathematics. So why do some believe that white holes could create universes? It begins by asking what happens when matter falls into a black hole. Everything gets pulled into the singularity, where space and time collapse, and the laws of physics no longer apply. Some scientists suggest that matter doesn't disappear entirely. Instead, the singularity could be a passage, a bridge, from this universe to another. From this perspective, a black hole in our universe could connect to a white hole in another universe. Matter enters on one side and exits on the other. As it emerges, it expands, forming space, time, and new laws of physics. And just like that, a new universe is born. Each black hole could be the seed of a new universe. Inside it, stars, galaxies, and even life could emerge. This idea is based on general relativity, the theory that describes gravity and the structure of space-time. It allows for extreme conditions inside a black hole to trigger the formation of a new space-time. Some physicists believe the very equations that describe black holes could also describe the birth of a universe. From this perspective, our universe didn't begin from nothing, but from a white hole in a parent universe. The Big Bang may simply be the result of matter and energy escaping from a black hole somewhere else, and if so, each new universe might carry its own physical laws, depending on the conditions of the black hole that formed it. For example, a larger black hole might create a universe with different matter and energy density. The way matter behaves inside that black hole could also affect physical constants like gravity or the speed of light. This might explain why our universe has the laws it does. Maybe this is just one of millions of other universes, each with its own traits. And if that's true, the universe isn't singular, but part of a branching system without end. Black holes are common in our universe. Most galaxies, including the Milky Way, have a supermassive black hole at their center. If each of these black holes creates a new universe, we could be living in a nested system of universes, linked across countless generations, each universe giving rise to another, a chain that may go on forever. And that raises a massive question. The Big Bang we see as the beginning. What was it, really? Maybe it wasn't the absolute beginning, but the natural result of a universe-forming process inside a black hole. A cycle where universes are born continuously, each giving rise to others. This not only reshapes how we see the origin of the universe, it also raises questions about the role of life in that process. If universes are born from black holes, could life influence that process? Some scientists speculate that advanced civilizations might intentionally create black holes to shape the properties of a new universe. It sounds far-fetched, but it shows the vast potential of the black hole-seeded universe hypothesis. It pushes the boundaries of imagination to places science once considered impossible. Still, this theory is extremely difficult to verify. We cannot observe inside a black hole. However, scientists are still searching for clues through how black holes behave and the structure of our current universe. For example, the large-scale distribution of matter and energy might hint at a connection to a parent universe. Studying black holes may offer insights into the extreme conditions required to give birth to a new universe. We may never see another universe, but mathematically, this idea aligns with what modern physics allows, and for that reason, it remains a theory worth paying attention to. If true, a black hole isn't just an endpoint, but a gateway to entirely new realities, a completely different set of physical laws. This idea forces us to ask, which universe are we really living in? And could our own universe have originated from a distant black hole, in another reality we cannot access? This isn't just some bizarre theory. It comes from the very equations of physics we use to describe space and time. If true, every black hole you see in the sky is not a dead end, but a beginning. A never-ending cycle of creation, where each universe carries the seeds of countless new ones. A structure like a cosmic family tree, with each branch being a reality of its own time, space, and physical laws. In this model, we are no longer the center. We are just one tiny node in a vast, invisible network of billions of other realities. And if we can understand how black holes truly work, we might decode the structure of the entire multiverse. The question is no longer how many universes exist, but rather, how many black holes are there? And what would happen if we created one? It would mean we just created a brand new universe, a completely separate reality, where time begins again and no one knows who you are. If you're looking for a different definition of creation, this might be the most fundamental one. Emerging from complete collapse. Black holes, long seen as the place where everything ends. But now, we're starting to realize they might also be where everything begins.